Hello, students, and welcome to Proving Angles Congruent.
With Mr. Carlson and Mr. Butterworth.
Yay! There's the applause and the canned yays and stuff. I'm just going to go to the next page.
Ooh,
Ooh, this is cool. This is called a theorem.
what is a theorem?
I would bet that a theorem is connected to that other word that we had, a postulate, because they sound alike.
I don't think they sound that much alike, Mr. Carlson.
That's fair. Maybe it's because they do similar things for us, where these are things that we can use as reasoning. But the difference is that a theorem we can show has to be true. And a postulate we have to accept without proof. I said without truth, that's weird. Because we don't have a mathematical way to show that it's true. We just have lots and lots and lots of examples that make it work. And we've already talked about this one because we're dealing with some vertical angles. So I'm going to take a look at what we're being told to do. So we're given some stuff with these two angles are vertical. I'm going to be like, yeah, I know, because vertical angles are angles that are formed where they are across from each other from the point of intersection. So those are definitely
obviously
vertical angles.
formed by two pairs of opposite rays, Mr. Carlson.
Yeah, but they don't have to be rays.
I know, but that's what the definition is.
I know, but okay.
I know they don't have to.
So what we're trying to do is to show that not only are these angles vertical, but they also are congruent. And I think you're going to find this to be a very similar process to some stuff that we've done over the past couple videos or video.
From like the last video we did.
So I'm going to try to state some other things that I notice here. I notice that we have some angles that are straight angles. So like if I take a look at angle 1 and angle 3, that those two angles together are what we call the linear pair. They are adjacent and they are supplementary.
Is supplementary the one that adds to 180?
It is. I know that because an S can be made into an 8 like that.
That's right.
So I might say something like angle 1 plus the measure of angle 3 is equal to 180 degrees. And I might even just say that because they're a linear pair.
Wait, can I do that for these ones also? The measure of angle 2 plus the measure of angle 3 is 180 degrees.
I think that makes some sense. It looks like the same thing we just did for the first ones. Is that for the same reason?
Yeah, that's why I smooshed it right in there.
Ooh, so we can use that reasoning for both of these things. And then something that I almost let slip the other day, but Mr. Butterworth stopped me, was noticing something kind of cool. That these two 180 degrees are equal to each other, because 180 degrees is always going to be 180 degrees.
Is this like that property that you love?
It is. So if we have one set of stuff is equal to 180, and another set of stuff is also equal to 180, then we can say that those sets of things must also be equal to each other.
And if that's confusing and you think of the transitive property as if A equals B and B equals C, then A equals C. If you read it as if you have stuff equals 180 and then 180 equals other stuff. I was going to come up with some other word, but I couldn't do it. I'm sorry. So I'm a math teacher. Then stuff and other stuff have to be equal. So if you want to kind of flip the syntax of what Mr. Carlson said to make a little more sense in your brain, go for it.
Cool. I like it. And I'm just going to say this is by the transitive property. Now, Mr. Butterworth, is there a reason that we couldn't call this substitution because we're substituting for 180 degrees?
No, I mentioned transitive because I knew you loved it.
Yeah, it's true. I do love it. And that goes back to my own geometry class in high school because my teacher was very excited by the transitive property. And every time we used it, he'd make us say transitive, transitive, ding, ding, ding.
That's a new story, Mr. Carlson. I have not heard that
I
one.
know. He was quite the character. I really enjoyed his class. Okay, so now we're stuck on this line of equation that, I know that we've got some things going on, and, oh, I have more things that are the same. Could we algebraically subtract these weird-looking things from both sides?
Yes, because that m, if that's confusing you, that's the measure of angle 3. That's just a number. Like, it's not a specific number in this case because we're doing a general statement, but it's just a number, like 17. So you're just subtracting that from both sides.
And that would leave us with the measure of angle 1 on the left side and the measure of angle 2 on the right side. Cool. And we also made a statement in the last video that if the measures of two things are equal, I almost messed up the wording there, that means that those angles or those segments, what we were talking about, must be congruent.
And we're trying to lessen the impact a little bit of some of the proof stuff, and we'll be emphasizing more of the algebraic stuff. So you will be solving equations where you're given one side and given the other side. And because they're vertical angles, then we've got equality and we can solve those equations, which might show up on the next page. Who knows?
Just to kind of, because this is a really big geometry thing, the fact that we have shown this has to be true without using any specific angles, without using any specific values for things, is a really powerful thing. And this is really unique to mathematics because it's only in math where you have something that you can show that things absolutely have to be true without exception. And there are reasons for that we're not going to go into. Most of them are philosophical. But what this means is that from now on, anytime that we see vertical angles, we can say, hey, vertical angles are congruent. And that's a really cool thing. Like here, where we have vertical angles, and we know that these two vertical angles must be congruent. Was there a delay on the...
There was a delay on the picture,
weird.
so you were talking about it, and we hadn't seen the picture yet. I mean, I had cheated and already looked at what it was.
Well, that's fair.
But it was pretty funny.
So these two vertical angles must be congruent, and we've already done stuff that's a lot like this. Because if these angles are congruent, we know we can make an equation, 2x
Is it
plus
similar
3.
to that bisecting thing, except different?
Yes, there's less Greek in this.
Okay.
I really should look that up to see if that actually is derived from Greek.
You've said it 3 times, so it has to be. It's a proof.
It could be Latin. I don't actually know. I've never taken either a Greek or a Latin course, but
Again, I just believed you. I should stop doing that.
Yeah. So we know that this is true, and this is true because vertical angles are congruent. I'm just going to call it VA for vertical angles. Best number ever.
My favorite number, 104.
That's weird.
Oh, I got excited.
Yeah, like, I'm sure there's a story there.
There really isn't.
Oh.
I have no idea why 104 is my favorite number.
Cool.
It just has been for as long as I remember. My second favorite number, 63 and a half.
You're an odd human.
You already knew that, friend.
It's true. So then you did some algebra to get to 104 equals 2x. And we can solve that and get that x is going to be 52. And I'm going to drive some students nuts by switching the order around.
If you got confused by the algebra I did while Mr. Carlson was writing down vertical angles are congruent, I subtracted 2x from both sides and I added 101 to both sides.
I like it. And then I divided by 2.
Yes. We have to be careful, Mr. Carlson, because it says solve for x and find all angle measures.
Oh, man. So we've got 2 different ones. Do you want to do the 4x minus 101? I'll do the 2x plus 3.
Sure.
So I know that x is 52. I'm just going to talk out loud. 2 times 52. Oh, I'm sorry, Butterworth. I should have given you this one. Because there's 104.
Took away my happiness.
I know.
I got 107.
I got 107 too. Wait. Did we need to do both sides of this?
If you want to make sure that you did the algebra correctly, then yes.
Oh, so if we had gotten different numbers, that would be a sign that something went wrong.
Mm-hmm.
That would be a really easy way to check for mistakes and try to figure out what went wrong while you were doing this problem.
And so if you wanted to explain in like a short little paragraph kind of what you did, you can say, I set up the equation and set the two expressions equal to each other because they are vertical angles. I used algebra to solve for x, and then I plugged x back into each expression and got the same number, which is good because vertical angles are congruent. Like if you could say that, awesome.
One of the things I'm finding kind of interesting, Mr. Butterworth, is that we talked about trying to make proofs less formal. And in doing so, I find that we're explaining our thinking more. And I think that's a really actual positive step in being able to explain things like this and what you're doing in each step and not have this be a formal proof.
I like it.
Oh, man.
Well, this next one looks scary, but if I think of the vertical angles theorem proof that we did, kind of the first, those things are dancing now. The first thing that I did,
I didn't realize I could move two things at once. It was exciting. I didn't know those were separate.
I know, we could tell because they were dancing back and forth. Anyway, then it kind of makes some sense because in the vertical angles theorem we had like 1 and 2, and then 2 and 3, and therefore 1 and 3 were the same. This is the same idea because it's saying 1 and 2 are 180, 3 and 2 are 180, so 1 and 3 are the same. And I've scribbled all over. I'm going to erase all of what I just did. But that comes, if we think about it, that comes directly from our vertical angles theorem.
So you're saying that we can do exactly the same thing to get to this point.
Yes, and really mathematically, you better put m's in front of those.
Thank you. I was being sloppy.
You were. But it's the same thing. And then you can say that they're equal to each other, and then you can say that 1 and 3 are the same.
Cool. I like it.
We should probably fill in that blank, though.
I'm going to say, oh, I can't write with an eraser. So if two angles are supplements at the same angle, I'm going to say those angles have to be friends. I mean congruent.
And if you're confused by that, if you're supplementary, you add up to 180. So if two things add up to 180, and then one of those things and another thing adds up to 180, they have to be, the pieces that are missing have to be the same.
I like
and then
it.
The same idea for the congruence. I had to read that theorem because I got confused because the name is the exact same and I was very confused.
Yeah, so this would be what we would call a corollary of this theorem, which is a logical next step based on the showing what we've already shown.
So the right angles theorem is silly. It just says all right angles are congruent.
Wait, but didn't we say that like we define angles being congruent if they have the same measure?
Yes.
And right angles are all 90 degrees. Yeah, that is silly.
I agree. Very silly. And then congruent supplements is I don't know why it has the same name. It's got to have a different name, but who cares? But basically, if we have what we just said up above.
Oh, no, I'm going to spell this wrong.
Good luck. And then 1R, 2Ls, is that how it goes? I don't know.
I don't even know.
But if the two angles are supplementary, but they're also congruent, then we've got to have right angles there. Okay.
1R, 2Ls. Woof.
We did it. So we can use some of those ideas, but again, we're not emphasizing proofs too much. So we might not see them quite as often as we might think. But we can use those ideas in some of our further explorations.